First of all, I would like to thank the organizer for inviting me to give a talk here, and especially to this community. I'm a total outsider. So I slightly changed the title from black phosphorus to black hole. Basically indicate conventionally we are material physics or condensed matter physics, jumping from black phosphorus material to black hole is a very big jump. So we have a lot to learn, and hopefully the experts here can give us some constructive comments and critical comments as well, so we know what to do next. What I'm going to talk about today is we have seen many analogs of black hole. So I'm going to propose a new type of black hole that based on we call it Fermionic Analogue, in a sense that we manipulate the electronic band structure or electronic properties in a solid state material that will mimic the black hole and simulating potentially Hawking radiation. Here I would like to first thank all my collaborators for this work being done. Feng Liu is a graduate student at the Institute of Physics of Chinese Academy of Science, who also visited my lab for 1 year during this project. And Hua Qinghuang is a postdoc with me, and now went back China, become a professor in Beijing University. And Jiatao Sun and Meng Shen are faculty members at the IOP, advisors of Feng Liu. And the funding of this project was supported by National Science Foundation of China and the US Department of Energy. Apparently, I hope this kind of collaboration can be continued in the future, which is uncertain for me to think now. As I mentioned, there are many analog, this workshop is devoted to the analog of black hole, and including, there are many different fascinating physical phenomena associated with black hole, and one of them is Hawking radiation. And one of the challenges of Hawking radiation is if we consider when solar mass, the temperature of Hawking radiation is 10 to the minus 8 Kelvin. And for that reason, we are studying analogs of black hole. And there are many proposals proposed and discussed, very interesting talk in this workshop. And despite the many progress and be made and the many interesting physics be revealed, there are also much more to learn and to study, and there are challenges such as, in general, all the analogs still have a very low Hawking temperature. And on the other hand, what I want to talk about today, get some background, is that in recent years, there have been many emerging study of topological physics in condensed matter physics or in solid state materials. And besides many other interests, there's one interest along this study is to use the quasi-particle excitations in solid states as an analog of high energy particle physics. For example, a very famous example is the Dirac fermions discovered in graphene. That can be described by a field equation just similar to the particle physics of Dirac equation, and so it's Dirac fermions. Now, if you break the time reversal symmetry, such as in a ferromagnetic material, and then this Dirac fermion equation reduced to the so-called real fermion equation, and furthermore, if you add a particle Hall symmetry like in superconductor, and a topological superconductor can have studied the Majorana fermions, and so in that sense, the solid state is an analog of particle physics. And talking about the Dirac fermions in condensed matter physics, it's just like a light cone, we call it Dirac cone. And there are different types of Dirac cone that lead to different type of Dirac fermions behave differently, which I draw here. For example, if the Dirac cone is upright standing, we call it type 1. And the Fermi surface is just a point, which is a Dirac point. Now, if you over tilt this Dirac cone, and then the Fermi surface will change to an electron and a whole pocket. And in between these two type of Dirac cone, and you can imagine there's one position where the Dirac cone with the edge which lie horizontal, and then the Fermi surface is become a line. Okay. And for convenience, let's say we name this one as type 3. And you can compare in the condensed matter physics community, let's say the topological properties and the transport properties of these three types of Dirac cones, and as I list in this table, and their topological properties are different for the, which are not of interest here, so I will skip. And on the other hand, there are many studies try to discover different type of materials that behave as a different type of Dirac fermion states. And most intriguingly, there are many material has been found with type 1 and type 2, and the type 3 is very rare. And 2 years ago, we discovered this material called zinc indium sulfide, which has exactly a shape of type 3 Dirac states, as I show here. So there's a horizontal line and there's a cross line with a Dirac point here formation. So in terms of using this fermionic analog, we call it of event horizon or black hole, our work is motivated by a paper published by Volovic. I think he's here at this workshop too. And basically, the idea is that if you look at these three types of Dirac cone, and it basically mimics the light cone across the horizon. Basically, inside the black hole, the light cone look like this, and at the event horizon, like in the middle, and the outside, will be black hole with upright cone, light cone shape, right? So for that reason, the velocity outside is lower than the speed of light and faster than speed of light inside. So similarly, this analog then can lead to a Hawking radiation, but it's a fermionic analog. Therefore, the interaction is strong. Therefore, the Hawking temperature may be much higher than the other analogs proposed. So here is basically again a comparison between the light cones and the Dirac cones. Okay, and inside the black hole is the event zone, event horizon, and outside the black cone. And if you basically fluctuate or tilt this cone at the horizon, then you have antiparticle and particle formation, and which lead to the Hawking radiation. And similarly, if we look at this fermionic analog, we have Dirac fermions. Inside hole is a type 2 type, and outside is type 1, and the horizon is formed by this type 3 type of Dirac semi-metal material. And then the separation of quasi-particle of holes and electrons will mimic the antiparticle and the particle. So now the question is how we can create in one material and three types of Diracons. The trick we propose to do is using so-called Floquet-Bloch Band theory or Floquet-Bloch states that are excited by laser. So first, as I mentioned, recent years there are many studies of topological band structure or topological materials, and here I list, for example, topological insulators, chain insulators, and Dirac semimetals, and there are also Ludoline semimetals. And of our interest here, apparently, is the Dirac semimetal that have the Dirac fermions. And these are typically the ground state properties of materials. That means at equilibrium. Now, if you shine for example, a laser, and there are the electrons absorb a photon, and then the electronic band structure changes, leading to so-called Floquet-Bloch bands, and and theoretically you can basically add, this basically adding a vector field of and you modify, you apply periodic time domain periodic vector field, or basically, then you can have this so-called a steady state solution by integrating over a period, and then you have you change your Hamiltonian, modify your Hamiltonian, and you basically I quickly go here. So you go from the Bloch bands to the so-called Floquet-Bloch bands, and then the zero states is the original band, and then if the electron absorb a photon, and the virtual band structure called index n equal to 1. If they emit 1, the virtual index n minus 1, and that's basically a constant shift of energy of the original bands. However, you consider the coupling between these different states, then you deform the band structure. For example, in one case, if you may open a band gap in the original Dirac band, that you transform a Dirac semimetal into a topological insulator, for example. And specifically for what we do is we actually developed a new computational scheme that can calculate the Floquet-Bloch states from first principles based on density functional theory. So what we do is we for equilibrium band structure is state of art is doing the density functional theory called first principle or AB initial calculations. And however, this method you cannot apply. You cannot apply an electromagnetic field or under the illumination. So what we do is we using a linear basis function to fit the first principle band structure. Then on this using this basis, we can adding vector potential to the Hamiltonian, and then if this potential is time periodic, and then you get the Floquet Hamiltonian, and you Floquet Hamiltonian, then you solve for what we talk about today. On the other hand, if this vector potential is not time periodic, you can actually, like a pump probe experiments, you can actually simulate the RPAS that stands for ongoing resolved photo emission spectra. To compare to experiments. So basically, we, in summary, we develop a scheme using density functional theory, plus the linear function fitting, and you can develop a first principle based Floquet theory to do all the band structure calculations or Floquet band structure calculations. Here are example which of interest today, which is a black phosphorus. And on the equilibrium band structure conditions without light illumination. And here on the top left is the structure of this material. And on the top right is the first Band zone I plotted. And this material is a narrow gap semiconductor. And however, if you compress it, apply a little pressure, and then they transform into a Ludo ring band structure. Ludo ring basically means there's a Dirac point on a circle. So it's like a Ludo ring. So it's a Dirac semimetal with a Fermi surface like circle formed by Dirac points. Okay, now if we apply laser and shining a light on it, as I show here by this vector potential dependence on the frequency at the time, then interestingly, this Ludo ring structure, band structure, transform into a type 1 Ludo point. That means you can imagine this ring shrinks into a single point. And because this dispersion relation is look like upright Dirac cone, so it's a type 1. Now you change the light intensity.
Sorry, 5 minutes.
Huh?
5 minutes.
5 minutes? Oh, okay, I will speed up. So you just increase the light intensity, then this type 2 become type 1 become type 2, and then in between there's a intensity is type 3. So basically, by tuning the intensity, frequency, and the angle of illumination, you derive this. You can calculate this phase diagram of different Dirac cone shape 1, 2, 3, right? And the physical reason for this is between, as I mentioned, between the coupling of the virtual Bloch band and the ground state, which I will skip. So then it can be, idea is very simple. So now if I have this material of black phosphorus, if I tune my laser intensity in different regions, then I can create all 3 types of Dirac cone shape in one material, as I show here. Then you can use this construction artificial structure but inside the electronic band structure changes from type 2, type 3, type 1, just to simulate the analog of black hole. And the type 3 will be the event horizon. And as I mentioned earlier, because this electron interaction very strong, we estimate the Hawking temperature can be up to Kelvin. So the last part is basically we transform this dispersion relation of this Dirac into light cone, basically in space-time coordinates, and then you can calculate the field, the gravity field in a sense for the Dirac electrons. Basically, the equation motion of electrons, all that. One interesting aspect of here is we can tune the gradient of light intensity. That means the region, the size of different regions of type 1, type 2, and therefore to tune the strength of this gravity field effectively. That can, in turn, tune the Hawking temperature. And how to get the spontaneous radiation is a question we don't have a good answer yet. And in this paper, anyway, we consider the case of quantum tunneling of electron and holes across this horizon between the 2 type 1 and type 2 Dirac cones. Then you can calculate the probability and find a Planck distribution of electrons and holes nearby, inside nearby this horizon. And based on this, we can then estimate the Hawking temperature, which is about Kelvin for the specific case we choose. That means the laser intensity and the distance of decay, or the gradient of laser intensity across a region about 200 nanometer. Which we choose these parameters because these are literature parameter that experimentally is feasible to do. And when possible to see this Hawking radiation is to because at the ground states these electron density distribution are Fermi-Dirac distributions, but with this quantum tunneling across the event horizon, you should see a peak of Planck radiation. So in summary, from the solid condensed matter point of view, we basically propose you can use laser to form a variety of Dirac fermions, type 1, type 2, and type 3. And we, for type 3, there's an intrinsic material of zinc indium sulfide, which have a very interesting type of bands, Dirac bands. And then if you can do this in one single material by tuning the laser intensity or frequency or angle of radiation, you can create an analog of black hole. And based on this black hole, potentially you can design some algorithm to observe analog of Hawking radiation. The possible advantage is the interaction of the system is very strong. Therefore, the Hawking temperature can be very high, up to a Kelvin. Thank you.
Thank you very much. So, questions, please. Yes, Justin, please go.
Yeah, thank you, Feng. So I have a question regarding sort of like the ground state for this Hawking radiation. So when you apply the laser to do Floquet theory, there's like two kind of similar problems, I guess. One is that you could heat the system up to infinite temperature, so you don't have a Fermi-Dirac distribution at all. The other is just that if you started with the Fermi-Dirac distribution and you apply Floquet, you don't exactly know, even adiabatically, where those electrons ended up in your band structure. You might have a very non-equilibrium system. So like, what?
Have you
thought about that?
We didn't consider the heating effect by laser. Yeah, that's a very, very good question. Yeah, there's a possibility of when you apply laser, the thermal. The Floquet theory is it's a non-equilibrium, but a steady state theory. So I think the electronic structure is modified and observable in the steady states. There are experimental evidence that have already observed Floquet band structure like a gap in the Dirac cone. But in terms of what we trying to propose here, I think you are absolutely right that thermal heating of the sample may modify the electron distribution, definitely. And I think the idea introduced by Volovic is very intriguing. Consider the electronic tilting of Dirac cone, and we propose one possibility to do here, but there are maybe other possibilities. For example, using strain effect, and also can tilt the Dirac cone in, but it's difficult to apply this different amount of strain in different part of material. So there are some challenges, but the idea is, I feel, is very intriguing to pursue.
Yeah, thank you very much.
Oh, sorry, you wanted to say?
Oh, I was just thanking him for answering the question.
Okay, so next is Jacopo, please.
Okay, yes. So I've just a general curiosity is a point that I did not really catch from the talk. So you are looking at the system which is prepared, except for Floquet issues, in the ground state, aren't you?
Can you repeat the question again?
So
Sorry.
this is except for the Floquet issues that Justin has just mentioned.
Yes.
So the system is anyway prepared in the ground state.
Yeah.
So, but normally, if I did not know anything about black holes, this would be a sort of strange material, which is a combination of different layers. So I don't see why there should be some transport of electrons around in the ground state.
Oh, I mean, so you apply a bias, let's say, that you have to do, will be an additional thing you have to do. You have to, as I mentioned, that there can be a quantum tunneling of electrons between.
Yeah. So you're not in the ground state.
Yeah, the ground state is a band structure to start with. And then if the Floquet works, you change the band structure into
of
3
course.
zones.
Yeah. Okay, good.
But then you have still to see the radiation. I think you still apply a pulse or a current through cross the sample. Just like other you create an analog, then you apply a wave, right? Then in the other analog you have to apply a wave to go back and forth. To see the let's say radiation or.
Okay, so there's a current.
Ground
Okay.
state construct the 3 different zones of, light Hawking or Dirac Hawking.
Mm-hmm. And then you impose the current to populate the bands in a suitable way.
Yeah.
Okay, thanks.
Yeah. Okay, I think we take last question from Jaakko. Sorry to other people who want to ask, but then we can continue in the discussion. So Jaakko, please. Jaakko Nissanen.
I can waive my question. It was discussed already partly.
Okay. So then next is Ted Jacobson, please.
Just a quick question. Do these Dirac fermions have a mass?
No. It's Dirac Hawking is linear dispersion, just like light Hawking.
Okay.
Okay, then let's take the last question from Jonathan. Jonathan, yes. Please.
Thanks. So do you have to worry, I'm wondering, do you have to worry about like a Dirac cone of opposite chirality? Like, I mean, in graphene, you have 2 Dirac cones, and I would be worried that they might cancel each other. Just float it.
Not, I don't think here, when we do the, honestly, fundamentally, as I mentioned, this is a fermionic analog. That means electron have spin and a different, the statistics is also different. But I don't think the 2 cancel out each other. I mean, that I don't think. Yeah, the transport properties of Dirac is well studied in the context of, condensed matter physics.
Okay, thank you very much.
By constant cancellation effect, for example.
Okay, I think we have to stop here. The time is over. So thank you very much for the very nice talk and discussion, and thank for all speakers of this very interesting workshop. Okay.